The screen recorder things were part of this program, right?
Mm-hmm.
So it won't record anything outside of that program?
It will.
It will.
It records anything I do on the computer. So let's do the definition. Definition of a function. Now, the definition you probably had last year is okay. I'm gonna give you a slightly more sophisticated version of the definition here in a second, but from what you know and what you were taught last year in Algebra 2, what would you say the definition of a function is? I kind of said it a few minutes ago. It has something to do with inputs and outputs. Something like that, right? For each input, there's exactly one output. So that we can write that down. That's not the actual definition the book has, but let's write that down. A function, so it's a relation. Now, a mathematical relation is just a way of relating two variables. You can relate a variable to another variable using an equation, using a graph, a table of values. Those are all relations. But a function is a specific relation in which each input has exactly one output. That's a pretty good definition. It works for the most part, but here's the definition out of the book. These are a little more advanced because it's college level math now, so sometimes it's a little bit hard to understand the definition if you just read it. So we'll talk about it. A function and they call the function f. A function f is a rule that assigns to each element in a set A exactly one element in a set B. This is pretty common. This is a pretty common definition of a function. Makes complete sense, right? We're ready to move on. Sometimes they're a little bit hard to understand at first. Let's talk about this. I want you to draw this. I want you to draw some googly little thing right here. We're going to call this set A. A set in mathematics is a set of numbers. It's a set that consists of certain numbers. Now over here, draw another little googly glob. We're going to call this set B. Now numbers contained within a set are called elements. Okay? We following so far? Which numbers are in set A? We don't know, and it doesn't matter. There are elements in set A and there are elements in set B. Are we okay with that so far? Now what a function is, it's a rule. So I want you to put an X here. This is one of the elements in set A. What is the element called? X. And what does X represent? An element, and it's just some number in set A. Okay? Now I want you to draw a line like that. This line is the function f. It's a rule. Now in mathematics, a rule is something, for example, this is a rule, x squared. So what if the function represents x squared? Whatever x is, what's the function going to do to it? Squared, and it's going to provide a new number in set B. So that's all a rule is. A rule is something that describes what you do to an element. Okay? Now, if I take x and put it through the function f, then the output is going to be f of x. This is exactly what this definition is describing. A function f, what part of this drawing represents the function? The line. Okay. Now what is the function going to be? It could be anything. It could be x squared, it could be 2x minus 5, it could be a quadratic function. Anyway, it's a rule that assigns to each element in a set A. So here's an element. The function took that element from set A, plugged it into the rule of the function, and what did it do? Give us a new element in set B. Okay? If you want to think about this set in different terms, this could be called the domain. The domain is the set of all inputs. So what could this set over here be called?
Range.
The range. Okay. What song? There's a song? Oh, the domain and range song, is that what you're talking about?
This person sang that song. This person I know sang that song to me.
I heard them singing. They were loud the other day. They were really loud. It's a good thing they. Anyway, let's go on to analyze. Or evaluate. We will get to that in a second. Not today, but. Evaluate a function. So, example 1. Now again, I don't want to spend too much time on stuff that you already should have a strong foundation on. So let's just do one example real quick of an easier evaluate problem, and then we'll get into some much more complicated ones. So if f of x is equal to negative 3 x squared plus 4x, and I ask you to find f of negative 2. Hopefully after these first couple of weeks and remembering what you did last year, you know what happens to this negative 2. Plugs in for all the x's. This is the input. And the input goes in for all of the x's. Really the main thing to keep in mind here is just your order of operations. You have to square before you multiply. You can't multiply the negative 3 and the negative 2 and then square. That's not order of operations. So negative 2 squared is 4. 4 times negative 3 is negative 12. 4 times negative 2 is negative 8. Add those together, you get negative 20. So your homework has a few of these easier ones. I try not to assign a ton of these because it's just, it's not something you guys need a lot of practice with, I hope. But let's try a little more complicated one. What if we had the same function, let's use the same f function, 3x squared plus 4x. But now I want you to find f of x minus 1. So now what happens? What happens with this x minus 1? We still plug it in for x. Whatever is inside these parentheses here replaces all of the variables. Here's the suggestion I would make you guys. Rewrite the original function, but anytime there's an x, make that into an empty parenthesis. So instead of negative 3x squared, this is negative 3 parentheses squared, and then plus 4 empty parentheses. And what fills in both of those empty parentheses? X minus 1. Okay, so we've made the substitution. Where a lot of students struggle at this point is simplifying. The substituting part isn't real complicated. It's to simplify. So what happens first? The x minus 1. We got to start with this x minus 1 to the second power. Now, I think I have talked about this before last week, maybe the week before. You cannot distribute the exponent to both terms. That does not work. X minus 1 to the second power means x minus 1 times x minus 1. There's a little shortcut. I know some of you guys are really keen on trying to learn shortcuts, the long way to do this would be to write x minus 1 twice, like this. And that'll work. That's not a bad way. And then you could just use the FOIL method. But the shortcut here, it's called squaring a binomial. If you square the first term, what do you get? X squared. If you multiply these two terms and then double it, if you multiply these two and then double it, you get minus 2x. And then if you square the last term, you get plus 1. Just a little shortcut there that always works. Distribute the 4 and get 4x minus 4. Distribute the negative 3. And then combine your like terms. This right here is the answer. Yeah. So what you need to gain from these two examples, you guys, if you evaluate a function at a number, f of negative 2, what was the result? A number. If you evaluate a function with an expression, what's the result of that? Another expression. Okay? Now, let's get a little more complicated here. Same topic. We're still evaluating functions, but there's a special topic here called the difference. You need to write this down. The difference quotient. I don't think you guys will have much trouble with this, but the college students I teach on campus sometimes struggle with the fact that 1050 is really only a preparatory class for calculus, is really the main point of 1050, 1060. So a lot of the topics we learn in 1050 don't really have any applied sense in terms of the real world. All we're doing is setting up a foundation for a calculus course. This is one of them, the difference quotient. I'm going to show you what it is. We're going to learn how to evaluate it, but we're not going to really learn how to apply it yet because we don't have the necessary skills. And that's the case for a lot of the 1050 topics.
Sorry for this interruption, teachers. We need those students with the last name F through J to report to the auditorium this time if they need pictures retaken. That's students with the last name F through J. Please report to the auditorium at this time.
So write this down. And this is something that you're going to have memorized. Probably won't provide this for you on a test, this formula. The difference quotient is f of x plus h minus f of x all over h. And again, you guys, the point of this is not to learn how this is used in the real world. This is simply to prepare you for what you're going to have next year in calculus. You're going to use this a lot, this difference quotient. Is anybody familiar with the idea of a derivative? This is the beginnings of how you learn how to take a derivative, is the difference quotient. Anyway, it just takes practice. It's kind of a mindless substituting plug-and-chug type problem. The problem is there are a lot of ways you could make small mistakes, and a couple of small mistakes early on in the problem add up to very large mistakes at the end. So just be careful with these. So let's let f of x equal 4x plus 9. Evaluate the difference quotient.
What is h?
Just h. We don't know the value of h. So let's do this one together. How I would start, always how I would start, is just with a big long fraction bar. There aren't many ways you can make a mistake in the denominator. What goes in the denominator? H. Most students usually don't mess up with that. So just put an h in the denominator. Where I would start next is on the right side of the numerator. Now, there are a few ways you can mess up here. What is it that we're subtracting on the right side? Now I'm going to write something that's wrong. I want you to tell me the mistake, because I see this mistake all the time. Aren't I subtracting f of x here? So how do I represent that I'm subtracting an entire expression? Because right now all I'm subtracting is a 4x. I'm not subtracting 4x plus 9. You do have to put it in parentheses, and that's one of the big mistakes I see students make. If you're subtracting an expression, you've got to subtract the expression in parentheses. So now what happens to the minus sign? Now you distribute it. Okay? It's this part on the left that's more mistakes are made. What is f of x plus h? Does this just mean that you add an h to the end of the f function so it becomes this? Is that what that means? What does it mean that f of x, what happens to the x plus h? It gets plugged in for anywhere there's an x. So f of x plus h is this function right here, but instead of an x, what do you write? So this becomes 4, and then instead of an x, it's x plus h plus 9. Now we go about simplifying. Distribute in the numerator, distribute everything, and then collect like terms. We have 4x plus 4h plus 9 minus 4x minus 9 all over h. Do you notice anything unusual? It does become 4h over h. Now let me make one thing clear, you guys. This should always happen. And if it doesn't happen, you've done something wrong. After you're done evaluating, anything that doesn't have an h should cancel. All of these terms that don't have h's, they should cancel with something else that's opposite. If you haven't done that, then there's a mistake that was made somewhere. Now 4h divided by h is 4. So the difference quotient is 4.
What does it tell you? The difference?
It's the beginning of how to find a derivative. In calculus, you learn how to find derivatives of functions like this. It turns out the derivative of this is 4, and that's equal to the difference quotient. So there are much faster ways that you learn in calculus to find the derivative. This is the long way, but it's the way that you'll start with. Let's try a little more complicated one. What example are we on? 2? Let's do part B. Let me do g of x is equal to x squared minus 4x plus 1. So a little more of a complicated function now. We have a quadratic function. So there are more, it's the same thing, you do the same exact thing, but there are more ways you could make simple arithmetic mistakes, so be careful. I want you to evaluate. Evaluate the difference quotient. If you listen to my suggestions, what do you start with? The bottom. Put an H. There we go. No mistakes made there, right?
Is it always going to be an h at the bottom?
Yep. Now what do? On the right side. Now if you want to skip a step, rather than subtracting the entire thing in parentheses, is there a way to maybe skip ahead and not have to do that? Exactly. Just change all the signs of the coefficients of the function. So you're going to minus x squared, but then you're going to add 4x, and then you're going to subtract 1. So if you want to skip a step and just automatically distribute that minus sign, you're welcome to do that. But I caution you, you've got to be careful of what you're doing. If you're the type that is prone to making arithmetic mistakes, you ought to just put some parentheses around it, just so you're careful. Now what about this left side up here in the numerator? We need to find, so the expression that goes here is g of x plus h. That's the expression that goes here. So what is g of x plus h? x plus h squared minus 4 x plus h plus 1. And then we have the wonderful opportunity of simplifying this. So just be careful. X plus h squared, you guys, is not x squared plus h squared. What is x plus h squared?
X squared plus 2x plus h squared.
But there you go. It's x squared plus 2xh plus h squared. And then you minus 4x minus 4a plus 1 minus x squared plus 4x minus 1. Now, if you were listening to what I said a few minutes ago, how do you know if you're doing things right? Everything in the numerator that does not have an h needs to be canceled. So the plus 1, the minus 1, the positive 4x, the negative 4x, the negative x squared, the positive x squared, those all cancel. So now let's rewrite this. We have 2xh plus h squared minus 4h all over h. Here's where we are now. Yeah. What happens next? Divide what by h? Keep going. Well, how do we do that? You're right. How do we do that, though? Does this cancel with that h, or does this cancel with that h, or what? Really, the correct way to do this, you guys, is to factor out an h from the numerator. So this becomes 2x plus h minus 4. And now the h that you factored out can cancel with the h in the denominator. So your final version, version 2.0 of the answer here, is 2x plus h minus 4. And again, just so you can make some connection to give you a point to all this, going back to the original function g, in calculus you learn how to find the derivative. Calculus pretty much is the study of two things, the derivative and the integral. The derivative is very important. The derivative of this turns out to be 2x minus 4. Does that bear any resemblance to the difference quotient? Very similar, right? There's just that h in there, so this is really important for your foundations of your understanding of calculus. So just deal with it. I know there's not a lot of practicality to this right now. Any questions on difference quotient? Okay. Here's a new type of function you need to be introduced to. So make him feel welcome. Piecewise functions. Everybody say hi. Hello. Some of you may have seen these before. Many of you probably haven't. These are not something that were introduced in Algebra 2. A piecewise function. The name's kind of cool. The name describes exactly what a piecewise function is. It's a function that's defined in pieces.
Very smart.
What's that?
Very smart.
Yes. Here's an example. Let's do, what do you got, example 3? Normally, now I want you to look up here for a second. Normally when you see f of x, you expect one expression over here, don't you? Okay. A piecewise function has a lot of pieces. So do your best to draw a little curly bracket like that. F of x, I'm going to let this one equal 2x plus 3 if x is less than or equal to negative 2. Over here, I'm going to say x plus 4 if x is greater than negative 2. So just so we can keep track of what's happening here, this column right here, the one I'm circling, these are the rules or the equations of the function. This is where you plug numbers into when you evaluate it. Okay, this right here can be thought of as the domain. Okay, these are the rules. If I ask you to find f of -5, I want everybody to stop for a second. Don't try anything. Initially, what students want to do is to take -5 and plug it into both pieces of the function. Okay? But what they're forgetting, and it sounds like somebody said it, what they're forgetting, what's the definition of a function? One input gives one output. If I took -5 and plugged it into both pieces, I'd get two different outputs. This would no longer be a function. So this -5 can only fit into one piece, and that's the reason for these domain definitions over here. If x is less than or equal to -2, you plug it into the top piece. What is x? They're your inputs, right? So what this is saying over here on this right side, if your input is less than or equal to -2, this is where it goes. If your input is greater than -2, this is where it goes. So our input, where does it go? -5 fits into this definition. So it fits into this piece of the function. So it's going to be 2 times -5 plus 3. -10 plus 3 is -7. That's how you evaluate piecewise functions. You need to always check your input and figure out which domain definition it falls into, and that determines which rule you plug it into. Okay? What if I ask you to find f of -2? Still plug it in the top one, because x is less than or equal to -2. It still fits into the top one. So 2 now times -2 plus 3. What do we get there? -1. Okay. And then if I ask you f of 4, what do we switch to now? Bottom one. Now our input would fit in this domain definition where x is greater than -2, so it has to fit in this rule, x plus 4. So this becomes 4 plus 4, which is 8. Now, in section 2.1, which is what we're on, all we're doing is evaluating. In the next section, we learn how to graph these, which is super fun. Okay? So just keep in mind. Now with this, you guys, with piecewise functions, this is not just some weird thing that mathematicians thought would be cool to come up with. These are used in practical applications. For example, this is kind of a contrived problem here, but if you go into a post office and you want to mail a package, okay, do they charge you the same regardless of the weight of the package? Don't they charge you more depending on the weight? So the post office may have something set up like this, where the cost, C for cost, they may charge you $10 if x is less than 10 pounds. They may charge you $15 if x is greater than or equal to 10 but less than 20, or they may charge you $20 if x is greater than or equal to 20, right? Something like that. And I know
You don't have a graph?
what's that?
You don't have a graph?
Then we'll learn. We do learn how to graph these, but piecewise functions are used. They're used a lot in business applications. Okay. So just keep that in mind. This isn't just some made-up thing. They are used. Let's move on. The most important part of this lesson. What did I say the most important part was? The domain. The domain is the set of all possible inputs. The set of all possible inputs. You did talk a lot about this last year in Algebra 2. Probably not enough, though. So we're really going to spend a lot of time on this idea of domain. So what example are we on? 4. Find the domain, and you do need to get used to this. I hope you're used to it by now, but you need to state in interval notation. We'll start off with some easier ones. Let's do f of x equals 3x minus 8. Now what you guys did a lot of last year is looking at graphs and finding the domain of functions based on their graph. You didn't really spend a lot of time finding the domain based off of an equation, which is a little bit harder to do. Graphically, it's pretty easy. Okay? With these, not so much. You just got to think about what you're doing here. What is the domain? It's the set of all inputs. So now you got to think, what kind of numbers could I plug in for x? And sometimes it's actually easier to think about what numbers can't you plug in for x. Are there any numbers that I cannot use as inputs for x? Can I use positive numbers? Could I use negative numbers? What about fractions? Could I plug in a fraction here? Decimals? Is there any number that will not work?
2 2/3.
2 2/3 would still...
What is that, the 8?
And 8 minus 8 is 0.
I was thinking of like,
in the denominator of a fraction?
yeah.
Yeah, we'll get to that in a second. That's a good thought. But what's happening to x? After I plug a number into it, what's happening to it? You times it by 3, right? Is there any number that can't be multiplied by 3 and then subtracted 8? If there aren't any numbers that don't work, then what do we say the domain is? What type of function is this, by the way? This is linear. What kind of a thing can we say about linear functions and its domain? They're always going to be all real numbers with one exception. There is one exception, and it really isn't a function. But what if I had a vertical line? Isn't that linear? But is a vertical line a function? No. But the domain of a vertical line is only that one particular x value through which that vertical line goes to. But anyway, if it's a linear function and it's has a defined slope, meaning it's not vertical, then the domain's going to be all real numbers. What about quadratic? Let's do g of x equals 4x squared minus 8. This is quadratic. Consider what happens to x once you were to plug some random number into it. If I plugged any random number into x, what's the first thing that happens to it? It gets squared. So now think, are there certain numbers that you cannot square? Can you square positive numbers? Can you square negative numbers? Can you square fractions, decimals? Are there any numbers that you can't raise to a second power? So what do we say the domain here is? For quadratic functions, what's the domain always going to be? All real numbers. For quadratic functions, the domain is all real numbers. So I'm not going to spend a ton of time on these because it's pretty easy. If you see a linear function, it's all real numbers. If you see a quadratic function, it's all real numbers. Can anybody think of a type of function that does have restrictions in the domain? Logarithms. Square roots. What were you going to say? Square roots. Let's get to square roots. Let's do h of x is equal to the square root of x plus 2. Matter of fact, let's make this even, since we have time, let's just make this even simpler and just do the square root of x. Sorry. H of x equals the square root of x. So, if you were to plug a number in for x, are there certain numbers which cannot be square rooted? Negatives. Right? Negatives cannot be square rooted. So this restricts our domain. It's no longer all real numbers. There are certain numbers that are not in the set of possible inputs. Okay? So how do we describe this?
Would it be bracket 0?
That's what we need to talk about. Is a bracket 0 or is a parenthesis 0? Can you square root 0?
Yes.
Depends on the way you think about it. It's practically the same controversy as dividing by 10. So, but when you square root something, you divide it by its square root, which would mean that you have to divide it 0 by 0. And it's division by 0.
What do we got to come to a consensus here. There is a right answer. Is 0 included or not?
I don't know. I think it's included.
What I'm asking you is this possible?
No. It's kind of like how 0 is like the bottom of the denominator.
I think it's possible.
Let me ask you another question. Why is this possible? Why is this possible?
It's 3 times 3 times 3.
Because 3 times 3 equals that, right?
Yeah.
So is there a number times itself that equals 0?
That square root of 0 is the same as dividing by its square root.
The square root of 0 is 0. So it is included. There is a bracket around 0. Where this is going to get a little more challenging is when the expression underneath the radical sign changes. So let's do f of x again. What was it I had there before? X plus 2 or something? Okay, let's do that one. Question for you guys. Could x equal negative 10?
No.
Could x equal negative 6?
No.
Could x equal negative 4?
No.
Could x equal any negative number?
Yes. Negative 2 and above.
Could x equal negative 2?
Yes.
What about negative 1?
Yes.
Yes.
So what's the smallest negative number x could be?
Negative 2.
Negative 2. And then how high does it go after that? To infinity.
And beyond.
Now we kind of found this reasoning our way to it. The algebraic approach is really what you need to understand here, because there are going to be some expressions where you're not just going to be able to reason your way to the answer. So take a look up at the screen, you guys. Regardless of what that expression is, let me just put a question mark here. Regardless of what this is, doesn't it have to be greater than or equal to 0 in order to square root it?
Right.
So the algebraic method is that whatever that expression is, no matter how complicated it is, you always take that expression and set it greater than or equal to 0. So in this case, what was the expression? X plus 2. So now you take that and set it greater than or equal to 0 and solve the inequality. If you subtract 2 from both sides, x is greater than or equal to negative 2. Now when you translate that into interval notation, it's from negative 2 to infinity. Now you may be thinking, well, I don't need to do this. I can always just come up with it in my head. And maybe you can, but these expressions are going to get a little more complicated. Okay? What about this one? So rather than trying to come up with it logically like we did in here, let's use the algebraic method. In order to square root this expression here, what has to be true of this expression? This whole entire expression, negative 7 minus x, it has to be greater than or equal to 0. Otherwise, you couldn't square root it.
So x is always has to be negative 7 or less than
Yes. How do we solve this? add 7. So now we have the opposite of x is greater than or equal to 7.
Divide what?
Divide by -1, and you do need to remember when you divide by negative to switch the direction. So x is less than or equal to -7, which means your domain is from negative infinity to -7. Any questions on that? For sake of time, I don't want to do a whole new example with this, but would it have made any difference if I changed this to a cube root? What do you guys think? The whole reason that we have a restricted domain is because you can't square root negative numbers. But couldn't you cube root negative numbers? What's the cube root of -8? -2. What's the cube root of +8? 2. So if I had changed this to a cube root, you can cube root any number you want, negatives and positives. So what would the domain of any cube root function be? All real numbers. If I went back and changed this to a 4th root, it's the same as a square root, right? You can only 4th root positive numbers. So what are we looking at here for the type of root? If it's an odd index, then it's all real numbers. If it's an even index, you have to follow this algebraic approach. Okay. Let's see how tricky we can get. One more root function, then we'll go on. We'll see how well you remember the last test that we took. What do we do here? We take the expression from within the radical sign, x squared minus 9, and what has to be true of it? Greater than or equal to 0.
Pardon this interruption, teachers. We need all students with the last name K through O that need to have their pictures retaken to report to the auditorium at this time.
Now, what a lot of students here would have a tendency to do is to add 9 in its square root. But that's not what happens here. Think to the test I just handed back. I gave you a problem similar to this, a quadratic inequality. Look at your test if you have it out. You do not just add 9 and square root both sides. You only do that if this were an equation. This is not an equation. It has to do with finding critical values and testing points. Does this sound familiar?
Yeah.
How does this factor? Factors like that, right? So then what are the two critical values? So you place those on a number line. Close circles on both. Now what? Test points within each interval. So to the left of -3, you could test -4 as a test point. What's -4 squared? And 16 minus 9? Is that greater than or equal to 0? So what does that mean about -4? It's one of the solutions, right? Because it worked, it satisfied the inequality. A number between -3 and 3, we could test 0. Does 0 work as a solution? What's 0 squared?
0.
And then 0 minus 9? That's not greater than 0. So is 0 a solution? This interval provides no solutions there. And then beyond 3, we could test 4. 4 squared is 16. 16 minus 9, that's greater than or equal to 0. So that is a solution. So the two intervals in which our solutions lie is less than -3, but greater than +3. So it's from -infinity to -3, bracket, Yep. These are the possible. Now, let's just check this. Okay. Plug it back into the original equation to make sure you end up with something that works. In this interval, let's try, I don't know, -6. Negative 6 is in this interval, right? If you plugged in a -6 for x, what's -6 to the second power? 36. And 36 minus 9? So it doesn't have a nice square root, but the point is, does it have a square root? Okay. But if you chose a number in this interval, 0 for example, and plugged it into the original function, 0 squared is 0, 0 minus 9 is -9. Can you square root -9? Well, none of these numbers work. So they end up with an undefined expression. Anyway, let's move on. We did radical functions. The other common type of function that gives you domain problems are rational. These ones aren't so bad. We've seen a lot of these. So this is example 5. Find the domain. If the function f is equal to x minus 2 over x plus 3, that's a rational function. Rational means ratio or fraction. Quite often with rational functions, there is only one number or a certain few numbers that are excluded rather than a whole set of numbers. What can't x equal?
-3.
So the domain you need to watch carefully to this. There are a few ways that I will accept these kind of answers. So the domain, x cannot equal -3, right? So if I were to represent the domain on a number line, if this is -3, everything is going to be shaded except -3, correct? So I'm going to put an open circle on -3 and then shade everywhere else. How do we represent that on an interval?
Negative infinity, -3
Parentheses.
with the
Union.
and then parentheses -3 positive.
So that's how you can represent that using interval notation. What does this mean? The entire number line is shaded except for what number? -3, because there's parentheses around it on either side. That's one way you can do this. This is interval notation. It's a good way. Okay, there's another way that's called set builder notation. This way is useful if you only have one or two excluded values. It's kind of nice. Set builder notation. What's this called here? Interval notation. You need to keep these two notations separate. This is called set builder notation. Okay? So it starts with a little curly bracket. So your domain, sorry, I forgot the word domain. The domain are all values of x. Now technically, if we want to be even more accurate, then maybe as our book goes, we need to describe what type of numbers x represents. What type of numbers does x represent? Well, not the interval, but I'm talking about the type of numbers. They're real numbers.
So would you do x is not equal?
So all values of x, then now draw a vertical bar. This means such that. So the domain is all values of x such that, and now state your exclusion. What can't x equal? So you'd say all values of x such that x does not equal -3. This is called set builder notation. So if you were to read this out loud to somebody, you would say all values of x, and what does this bar mean? Such that x cannot equal -3. So set builder notation works well if you only have a few excluded values. Okay? Let's try part B. G of x is equal to x minus 8 over x squared minus 2x minus 8. suggestions?
Factor the bottom.
You do have to factor the denominator. Yep. So it's x minus 8 over
X minus 4.
x minus 4, very good, x minus 4, x plus 2. Now, what is the domain going to be? What can't x equal? X cannot equal positive 4, and x cannot equal negative 2. So let me show you two different ways to write this. Whatever way you want to do it is up to you. If you want to use interval notation, you would write it this way: domain. You always start with a smaller number, negative 2. So it goes from negative infinity to negative 2. Union, negative 2 to 4. Union 4 to infinity. Essentially, what does this mean that I've written this way? Every single number is in the domain except for which two numbers?
Negative 2 and 4.
Negative 2 and 4. Everything else is in the domain. That's interval notation. Using set builder. What is the domain?
X.
It's x such that
X is not equal to negative 2 or 4.
x does not equal negative 2 and x does not equal 4. Okay, last one, then we're done, I promise. This will be our last one. Your book gets really tricky and tries to combine these two types of functions. They put a rational function with a radical function, which is crazy. So now it's both. It's rational and there's a radical in there somewhere. Here's what I would suggest. First of all, consider just the radical part. For the time being, forget about that it's in a fraction. So don't worry about the denominator. If this function were just the square root of x minus 2, what would the domain be? If it were just the square root of x minus 2. Wouldn't you take the expression x minus 2 and set it greater than or equal to 0? Now, I don't want you to solve it yet because this isn't actually the domain. Now we do need to consider the fact that it is a fraction. So this would be the correct domain if it were just a radical function, but now we have to consider the rational part of this. Is it okay for this expression x minus 2 to equal 0? Because if x minus 2 equals 0, then what's the square root of 0? 0. So there's only one thing that's wrong about this.
You just make it not greater than or equal
It has to be greater than.
It just has to be greater than. Okay? It has to be strictly greater than 0, because if it equals 0, you end up dividing by 0, which makes the expression undefined. That's the only difference. It's no longer greater than or equal to, it's just greater than. So x is strictly greater than 2, which means your domain not negative 2, would just be
Sorry, 2.
positive 2. It would be parenthesis 2 to infinity. That's the only difference.
Okay.
Just so we're clear, why did I not put a bracket around 2? Well, if I plugged in a 2 for x, what's 2 minus 2?
0.
Square root of 0 is?
0.
0. So you cannot include 2.
Two.
Okay. All right. That's the end of 2.1.